Okay, hello everyone. I hope you all had a great fresh start into the new year and also recovered from the ICML deadline. So it's my great pleasure to introduce Subho today as our speaker who kicks off the new year. He's a principal scientist at Microsoft, and his research is mostly focused on efficient learning for massive neural networks. And yeah, today he's going to talk about NAS for efficiently sparse activated transformers. So with that, stage is yours.
Thanks a lot, Aaron, for the introduction and also for inviting me to present this work. So hi, everyone. My name is Subho Mukherjee. I'm a principal researcher at MSR Redmond. So this is a joint work with several of our collaborators from University of British Columbia and MSR. And a large part of this work is actually driven by my intern, Ganesh, who was working with us last year. So today I'm going to talk about neural architecture search for sparsely activated transformers. Okay, to start with, so let me give you a brief background into why we are interested in this. So we have seen slides like this number of times before. So human brains are modular and plastic. So they're modular because they're composed of distinct and interacting modules, each specializing in different kinds of functions. They are also extremely adaptive, as these modules can be pruned and joined on demand, as we learn from various experiences and interactions around us. So we are interested in incorporating many of these principles into designing efficient neural networks. So, in traditional dense models, so this is a diagram of a traditional transformer, and you would be quite familiar with this. So in traditional transformers, the entire network is activated for every input. So here, this computation is typically said to be non-adaptive. Non-adaptive in the sense that we use the same amount of computation for every input and task. Also, to make the talk more interactive, please ask me questions in between. Just raise your hand and I would be happy to engage. So we think that adaptivity is one of the important components that we should be designing in the neural networks. So as opposed to the traditional dense models, we also have the existing sparse models. So I would explain like how sparse model works, but on like to give a very high level overview. In sparse models, what we do is we route input token to different modules in the neural network. So this allows us to use the same amount of computation, but also more number of parameters in a dense model. For instance, in the previous case, in traditional transformers, you would see that there is a single feed-forward neural network block. In say an AutoMoE implementation, you would just not have one, but multiple FFN blocks, and you would be selecting different combinations or a subset of them based on the context of the input. So what modularity allows us is to have structured sparsity, and these modules can be thought of as a functional unit for compositionality. For example, you could think of these modules as specialized in different kinds of tasks. If you were to use, say, a multitask version of these AutoMoE models. These modules could also be a computing unit for hardware optimization. For example, in say methods like G-shard or similar implementation, you would see that similar of the experts would be often put in a single device to reduce the intra-expert communication cost. Now, the AutoMoE models, although they enable us to use different amounts of computation, they're still non-adaptive because the same number of model parameters are activated for different input. So for instance, if I were to use, say, top 2 experts or top 1 expert for every input, so in principle, since all the experts are of homogeneous sizes, I would still be using the same number of same number of model parameters that would act on any single input. So that makes it non-adaptive, and this is largely given by the homogeneous nature of designing these AutoMoE models. Now, why are we interested in sparse models? So in several of the recent works, the sparse models have been shown to outperform flopped match dense counterparts. So even from Facebook, if you look at papers like OPT and OPT AutoMoE, you would see like impressive performance of the OPT models when their flops matched to their traditional dense counterparts. Okay, so now to give a brief background into why mixture of experts are different and what are the different things we need to consider before we even talk about how to use NAS to extract efficient subnetworks. So there are two important components in a mixture of experts network. So the first one are the experts themselves. So recall that in traditional dense transformers, you had a single feed-forward or FFN block. In case of a mixture of experts model, you are going to have multiple parallel feed-forward network blocks, which we call the experts. Not all of them are going to be activated at the same time. So we will activate only a subset of them. And this decision is made by a router. So the router produces is a trainable gate, which produces a routing probability for the different experts. And depending on our routing policy, for example, if I were to use top 1, I would use the maximum activation to select a corresponding expert. I could use also top 2. There are different variations of the same. For example, there is a work recently from our collaborators who introduced this notion of random routing, where you could select 2 experts randomly, and then you would use some kind of consistency regularization of top to minimize divergence and so on. So there are different variants of the routing protocol. So for the remaining part of the talk, I am primarily going to focus on the switch transformer routing policy, which is given the router probability distribution, I'm going to do top 1 expert activation. So now for the mixture of experts, there are several design choices. So first, the expert placement. So where do we introduce these experts? So if you look at existing MOE literature, the most popular one seems to be introduced in alternate layers of the neural network. For example, say 2, 4, 6, 8, and so on. Some papers like STMOE, they place the layers after every 4 layers or so on. But why should we do that? Can there be any principle by which we can design this? Also, in this specific, like in this part of the talk, I'm going to focus on encoder-decoder models, and I will shortly explain the setting. So in encoder-decoder models, you have an additional dimension, like should you place experts differently on the encoder versus the decoder, and why would you make one choice versus the other? The second thing is about the number of experts. So how many experts should you introduce in the model? And you could also incorporate some notion of heterogeneity, for example, variable experts in different layers. For example, should you put more experts in the lower layers versus the higher layers and so on? And we would again want to have a design that gives us a principled policy. So the last thing is about the size of the experts. What should be the intermediate size for this feed-forward network block? So these are the 3 core design choices that you have for a mixture of experts model. Now, if we consider that there are m experts, n layers, and n possible sizes, it leads to an astronomical number of possible design configurations. And remember that this is just for the sparse search space. If you also consider the dense part of the search space, that is, you can have variable encoder layers, you can have variable decoder layers or attention heads, and so on. This results in million more configurations. So again, we would want to have a principal design policy to navigate through these all these possible combinatorial choices. So first of all, like, why do these choices even matter? So here, in this example, we show a MOE network. So here the task is a machine translation task in WMT14 END. So you have an encoder-decoder network. Consider a setting in which we have manually designed this network. So it's a 6-layer encoder-decoder, and assume that we have put 4 experts in each of the layers. So that is why you have 4 times 6 number of experts on the encoder and corresponding on the decoder. We measure the neural machine translation task performance in terms of the blue score. We show the latency here, which is measured in a single CPU. We show the active parameters. So again, remember that the MOE network can be very large, but not all of the parameters are active at the same time. How many parameters are active is dependent on what routing policy you choose and which expert you choose. In this case, we are activating only 1 expert at a time, and then we also measure the flops. So there can be another configuration in which we can inject the experts in every other layer. So you have one expert in the first layer, 4 expert in the second layer, and so on. As you can see that the number of active parameters and the flops are the same, but the latency is going to be different. Again, the latency is incorporated by the additional communication cost and the softmax activation that is required to select which of these experts that we are going to invoke and so on. Now, for instance, we could use some policy like AutoMoE to come up with the best possible configuration of this network. So example, what AutoMoE does here is it decides, okay, I'm not going to have 6 decoder layers, I am going to have 4 decoder layers. So removing the decoder layers massively cuts down the latency, and we will again see why that happens. Now, when it cuts down the decoder layers, it also compensates for the capacity loss by injecting additional experts on the bottom decoder layers. Again, this is something that we wouldn't want to do manually, and we want to have a framework which automatically figures out these configurations given some latency constraint. For example, the latency constraint here was 600 milliseconds, and it came up with the best configuration it could find within that constraint. So in terms of the blue score, you see that this almost has parity. Least number of active parameters and flops is what we want. Okay, so AutoMoE, this is the first work to automatically design efficient sparse transformers. So let me know if you have any question so far.
Yeah, quick question. If you go back to the previous slide, so your mixer, so your MOEs, they're always the same size, right? Or do they have different sizes?
So which size are you talking about? The expert sizes?
Yeah, the expert sizes, yes.
Yes, the expert sizes are going to be variable, and I will show the search space.
Oh, okay, I see. And in your routing protocol, so you always just choose one single expert, or could you also use multiple experts at the same time?
You could use multiple experts. It just depends on how you are training the supernet. Yeah, I will come to the training point. So this is just kind of the background.
Okay.
So,
yeah,
okay,
thanks a lot.
Thanks, Aaron. So, okay, so let us look at the search space first. So what is a search space is basically what are the different knobs that you are going to tune to find out this efficient sparse subnetwork. So it has 2 components. The first component is the dense part of the transformer. And again, the dense part of the subnetwork is something novel. It has been explored earlier in papers like, say, the hardware-aware transformers, which was in ACL year or 2 back. In AutoDistill, which was our new RIPS paper last year. So in the dense search space, you decide how many encoder layers are you going to use, how many decoder layers, the QKV dimensions, and so on. So there is an additional component that the HAT paper also introduced is which decoder layer, which encoder layer are you going to attend to when I am decoding the tokens one by one. So the traditional principle is the last decoder layer, but it could also make it a searchable node. So what AutoMoE does, it is overlays the sparse search space on top. So how does a sparse search space look like? So it has primarily 3 dimensions. The first is where you are going to inject these experts, like how which of the layers should I choose to introduce how many experts. The second dimension is the intermediate FFN size, which Aaron was just asking about. Can we make the experts of variable sizes? So for example, in this case, we show that there are 3 possible sizes that we are exploring. So the right-hand side configuration shows which is a transformer base, and the second optional dimension will show the big transformer big, again, manually constructed, and which wherever they vary. So the final thing is how many experts I'm introducing in each layer. So we do have one hyperparameter here, which is capital M, which is the maximum number of experts allowable in any layer. For instance, in all of these works, we assume that capital M equal to 16. So 16 experts are the maximum number of experts allowable in any layer. And AutoMoE, what we would try to do is find a subset of them of variable sizes and also the layers where we are going to place them. So this is the sparse search space that we are overlaying over the dense search space. So again, as we are deciding which layers to put, these layers also are of variable dimensions given by the QKV, and also like we could have variable number of layers. For example, instead of 6 decoder layer, we could have 4 decoder layers. So the dense search space and the sparse search space are really interacting with each other. So here you have the notion of adaptive compute. So what does adaptive compute mean? We are going to use different amounts of computation for different tokens in the input. Now in this, our framework, the adaptivity primarily comes from routing the tokens to experts of variable sizes. So again, like the last block, we have experts of variable, intermediate, hidden sizes. So even if I am choosing only one expert in different layers, I could have experts of different sizes. So my tokens are really going through a different part or subset of the computational graph at different points in time, which gives it the adaptive compute capability. Let me know if you have any question on the search space. Okay.
Subho, one quick question actually. So in general, the limitations of the MOE models is that they are more complex and they have some expert bias. Any comments on that? Like how does AutoMoE addresses any of these, or is it the same issues that are there with typical MOE models?
Yeah. So AutoMoE again inherits the switch transformer. So if you have to train some model like a switch transformer, Glamour, G-Shard, it would inherit similar dimensions and search spaces. So essentially it would incorporate similar biases. So if your question is, are the biases amplified when we are compressing the network? So that is a different question. So for example, we just have a paper recently where we are exploring what happens to compressed student models, whether they are more robust adversarially or otherwise compared to the large model. And there we see some evidence that the smaller networks learn some shortcuts in the data. So in general, bias could be amplified, but this is kind of a different dimension than the efficiency dimension that we're talking about here. Does it answer your question?
Yeah, I think so. Yeah, thanks.
Thanks. Okay, so before I go into the AutoMoE training, I'll touch briefly on super language model training. Again, super language model training is nothing new. It has been used in prior works like, say, Big NAS in the CV domain, even HAT in the natural language understanding domain and AutoDistill. So how does super language model training work? So here our purpose is to train a very large language model, which is called a super language model. And the super language model is composed of many child models. And these child models have shared weights and dimensions. For example, you can consider of a 12-layer model, which is composed of an 8-layer model, composed of a 6-layer model, and so on. And they also share all the other dimensions like the number of attention heads, width, and so on. So assume that I'm able to train this large super language model in a compositional way. Then what we could do is we could sample several child models. There is also a sampling policy involved here, like whether you are using the sandwich rule or you are just randomly sampling. Assume that you have sampled some child models. Now we could train these child models for a few steps. We could collect the gradients, put the weights back into the super language model. Then we again sample the child models and collect gradients and update the super language model. And this process goes on till convergence of the super language model. So here the super language model is really trained by weight sharing of these child models. Once the super language model is fully trained, any child model that I extract from the super language model is going to be fully trained as well, which means I don't need to really fine tune it. I could just apply the child model to any downstream task and evaluate the performance on the fly, which gives this technique a particular advantage, which we will shortly see. Okay. So how does this work in the AutoMoE space? So the part one, the design space construction, which I have already talked about, like what are the different knobs that we are tuning. So the first part is, given this different search space, we will sample an architecture randomly from the search space. And the second part is I'm going to use this for super language model training. So let me first also discuss the architecture of the super language model. So here we have an encoder decoder framework, right? So we are going to see most of these results on a machine translation task, which is an autoregressive decoding task. So we are going to feed the input through the encoder, get the representation either from the last encoder layer or say the K previous encoder layers, which would be a searchable knob. Then it would go into the decoder, which would decode the tokens one at a time. So the typical, like the embedding size, self-attention heads, etc., these are part of the dense search space. What the AutoMoE uses on top is the notion of a router, which given a token would decide which of these FFNs which are the experts. So you have AIM FFNs corresponding to the AIM experts. It would decide which of these experts to send this token. And again, these FFNs could have variable sizes, as you see by the grade shade. Now, the same principle would also apply on the decoder side. So this is how the super language model would be trained in general. So now what do? We sample an architecture randomly from the search space. Then we will train the sampled architecture by subnetwork weight extraction. So this is the most critical part, which I will focus on the following slides. So when I'm extracting my subnetwork, my child network will inherit the weights from the super network. So the most critical part here is how do you extract this subnetwork? Assume there is some way to do that. Then I would train that sampled architecture for one training step, and then I would repeat the steps 1 and 2 till your training budget is exhausted. For example, you decide to train this for 40,000 steps, and that would be your training budget. Okay. So now the most critical part is the subnetwork extraction, as I said, because the entire super language model is trained by weight sharing. So subnetwork extraction again has two components, the dense part of the network and the sparse part of the network. So first, let us talk about the dense network. So suppose you decide to sample an architecture where you have the number of layers and the hidden dimension and the heads. So a very simple way to do that would be by truncation. So suppose you had a matrix or the embedding size of the super language model, which was say 1024, and you decided to extract a subnetwork with embedding size 512. So you're going to retain the first 512 elements from the left of the super language corresponding matrix on the supernet. And similar would apply for the number of layers as well. So for example, this shows an example of a bottom left submatrix extraction. So this truncation is a very simple way to allow the child model inherit the weights of the super net weight matrix by simple truncation. There could be other sophisticated policies as well, like for example, skipping dimensions and so on. But for the purpose of this talk, assume that we use a very simple policy like this. So this would apply to the dense component part of the network. And again, this is something that is not introduced by this work and has been done earlier by most of the works which use super network training for dense transformers in general. Okay, so what AutoMoE introduces are the MOE components, and there are two MOE components in particular. The first one is the router. So what does a router do? The router decides to send each token to one of M experts. Again, capital M, assume it to be 16, which is the super language model. Maximum number of experts allowable in the super language model. So when we created the super language model, it is the largest network which is available in the space. So the super language model has full 6-layer encoder, 6-layer decoder. All dimensions are to the full. For example, we would introduce 16 experts in every layer of the super language model when we are training it. Okay. So the purpose of the router is to send a token to one of the 16 experts. Now, consider that you have a super language model with 4 allowable experts. So 4 is the maximum number of experts that is allowed in any layer. And assume that 640 is the maximum embedding size. Again, when we train a super language model, we consider all the dimensions to be full. So then the routing matrix dimension would be 4 times 640. Now, suppose we are extracting a subnetwork or a child model where we decided to sample 3 experts with an embedding size of 512. Again, we could do a simple truncation of the super language model. So 4 times 640, we are going to extract a submatrix of dimension 3 times 512. And we could do this by simple top left or bottom left extraction, whichever you want to choose. So this is how you are going to obtain the router submatrix of the subnetwork from the super language model router matrix. So the second component that you have are the experts in the MOE space. So how would the MOE extraction work, the expert weight extraction work? Again, a similar principle. So the experts are, again, you have M. In this case, you have, say, 4 maximum allowable experts or FFNs. So these are transformer blocks with unique weights. So consider that you have the super language model where you have 4 experts and the maximum embedding size is 640, which we saw before. And consider that the experts have the intermediate size of 3072. Now you decided to choose a subnetwork with 2 experts. Remember that we have variable size experts. So maybe you sampled an expert which has intermediate size 2048, and the embedding size 512, and the and correspondingly for the other one, and we could apply the same principle and obtain the subnetwork weight matrix by simple top left extraction of the corresponding weight matrices. And remember, whenever we are doing this metric extraction, it assumes that there is a certain routing policy that is involved, which chooses these experts. And as I earlier mentioned, we are employing the switch transformer routing policy in this case, which is top one expert activation. Let me know if you have any question on how we extract subnetworks from the super network. Okay. So now once my super language model is fully trained, again, how am I training the super language model? I had these designs, I had this search space, I randomly sample an architecture, I extract the common parts of the weight from the super net. How do we do that? That I explained in the last few slides by weight sharing. I will then train this subnetwork for a few steps, put its weight back into the super net, and this process will go until convergence. Once the super language model is fully trained, then we want to extract an efficient subnetwork. So now I'm going to talk about how do we search for the optimal sparse subnetwork. So in order to do that, you again have like 3 steps. First, we will sample various architectures. Now we want to evaluate the task performance. One of the advantages of the super language model training is once it is fully trained, any subnetwork that I obtained is also well trained. And I could simply apply it on the downstream task, for example, say machine translation task. So there is no training or fine tuning involved for the child model. And I could simply obtain the performance on the fly. Again, for the subnetwork, I also need to measure some notion of efficiency. For example, the flops, I could have a closed form formulation of the flops. If I were to measure latency, I could also do it on the device and so on. So we will also see what are the different search constraints that we can invoke on the child model shortly. So I assume that we can evaluate the task performance. So these would also give me kind of good candidate subnetworks. If you want to get more refined candidates, then there are methods like you could use crossover and mutation, which are again some of the techniques employed in traditional NAS papers, for example, the big NAS, AutoMoE, and so on. And you could further refine these subnetworks that you are obtaining. Okay, so now the primary constraint here, once you get a subnetwork, how do you decide if it is feasible for your use case or not? So what do you search for? So there are primarily 4 constraints that you could search for. The first is the flops. So as I showed before, in the AutoMoE world, you could have multiple subnetworks with the same flops, but widely varying latency. And as you will see in one of the experiments, that flops is not a good constraint for search. And typically, if you give any flops budget, the search method would always exhaust the full budget and lead to a subnetwork which has a higher latency. The second most commonly used method is a latency predictor. So what is a latency predictor? Consider that you have a 3-layer MLP that you are training offline. The input to that MLP are some network architectures, and the output is the actual on-device measured latency. The idea is if you have offline trained such a latency predictor, then when you are doing search for an efficient subnetwork, you could feed the candidate architecture to the latency predictor, and it would give you an estimate of the latency. So what we found out is for AutoMoE, the latency predictor is super noisy. So as opposed to the dense transformers, these sparsely activated transformers have a lot of stochasticity involved in the generation process. So there are primarily 2 things in our setting, that we have a fully heterogeneous search space and we have experts of variable dimensions and sizes, which means that for each of the tokens that you are sampling, depending on the context, you are going to invoke a different part of the computational graph, which invokes stochasticity and makes the latency predictor quite noisy. So the third thing that you could do is you can actually go to the device and measure the gold latency. For example, you decide that I'm going to do, say, a large number of passes, forward passes, given an input on the device, get the latency, truncate to remove the outliers, so the top and bottom 10% of the latencies, and compute the mean on the rest. What we use is a variant of that, which is a partially good latency, means I'm not going to do so many passes. I'm going to do a few passes. There would be some noise involved, but we are happy with that just to make the process faster. And we show a trade-off of how many passes versus the performance, etc. in some of the experiments. Okay. So now in the previous one, we saw what are the search constraints you could use to extract the subnetwork. Now, once you obtain the subnetwork, you again have two choices. So remember that the subnetwork shares weights from the supernetwork. Once the supernetwork was fully trained, my subnetwork was also trained. So I could simply inherit the weights. And I could continue training if you want to improve the performance further. Or you could throw away the weights. You have the skeleton architecture and you can train from scratch. So neither of these methods have a lot of advantages on top of each other if you have a fixed training budget, and both of them kind of give comparable performance based on the experiments. So now, before I go into the experiments, let me know if you have any questions so far on the algorithm.
Yeah, I have one question is about the sampling of the subnetworks. So is this just random sampling, or do you do something more advanced? I think you mentioned the sandwich rule. Do you do?
Right. So in this case, Aaron, we did not use the sandwich rule. We just use random sampling here, and we will actually see a random search baseline, and you will know, like, the random search really gives you very strong and efficient candidates. In this work, we did not use sandwich rule. In the AutoDistill paper I mentioned, which we had in NeurIPS last year, we use a sandwich rule, which is essentially take the largest subnetwork, the smallest, and any two random in between, but not in this work.
And do you have any experience on? So do you do anything like I think they had this in the big NAS, right, where they ramp up the random sampling procedure. They start, I think, with the training the full network and then ramp up the
no.
mobility.
So in this case, we assume that okay. So the assumption is that first you could train a switch transformer from scratch. It's 40,000 training steps, which is kind of our ceiling performance. And we use the same set of hyperparameters, same, say, warm-up, learning schedule, and so on. You could actually tune a lot of these hyperparameters to improve the performance. But our setup is you have the same training budget for all networks, same hyperparameters, no tuning, and then what is the best performance that you can get.
Okay. And last question. So you mentioned evolutionary algorithms here. Have you also how much impact does this choice have? So if you would tweak the evolutionary algorithm, or if you would use something else, I don't know, would that work better, or would that matter? Wouldn't that matter?
So I can partially address this question. Like, if you were to do random search, like random search means essentially you have the AutoMoE search space and you randomly extract a lot of subnetworks, which matches your latency constraint. And then I were to train one of them from scratch. So this is one setting. Okay. And the second setting is when we are doing the super language model training plus the evolutionary search, what is the performance? And we would want to beat the previous one where we see a combined gain. But we do not have a specific ablation test, which ignores step 3 and just sees how much benefit it brings. This is something that is missing and wanted to do, but yeah, haven't done it yet. Yeah, my kind of intuition is, since the random search performance is very good, the supernet training itself. So you do the supernet training and then you extract a random subnetwork that would itself give you a very competitive candidate. Maybe the crossover and mutation like the GA would give you some benefit on top, but I don't expect it to be a massive benefit.
I see. Yeah. Okay. Yeah. Thanks a lot.
Awesome. Thanks, Aaron. Okay. So what is the experimental setup here? So here we take, say, 3 traditional benchmark tasks from neural machine translation. So task setting is, we are going to have a bunch of models that we will see shortly, and we are going to train all of them for exactly 40,000 steps. So yes, you wouldn't see SOTA performance in general, because typically SOTA models are trained for 90K or 100K steps and so on, with a lot of hyperparameter tuning. We are also not going to do any hyperparameter tuning. We typically inherit most of the say hyperparameter configurations from the HAT paper, which is built on top of the FairSec toolkit, and we use both of them, and we incorporate all the things that I have said so far on top of that. So also another important aspect when you are training for a neural machine translation task is the effective batch size. So we're going to train all these models on 16 V100 GPUs, and we have an effective batch size of say 500,000 tokens. So the effective batch size is essentially given by say the gradient accumulation times the number of samples per the batch size per GPU times the number of GPUs. So these are going to remain invariant for all the models that we will see so far, next, for a fair comparison. Okay. So don't get daunted by the table. I'll actually dive down into deep details for each of them. So again, these are like 3 tasks and a lot of different dimensions. So just to keep it kind of simple, let us focus on a specific task from this set, and the trends are comparable. Okay, so the specific task that we are showing here is the WMT14 English to French machine translation task. Okay, so we are going to compare, we are going to ask 2 or 3 research questions, and we are going to evaluate them on multiple dimensions. First is what kind of network is the best? Should you use a dense model, sparse model? And if you have to use a NAS, what would you use it over? So the active parameters, again, as I said that in a MOE model, not all the parameters are active at a time. So you should read the active parameters along with the sparsity. So sparsity is the ratio of the non-active to total parameters. So in case of dense models like transformer big or any of the NAS over dense models like evolve, transformer, and hat, the sparsity is 0 because you are activating all the parameters. The MOE models like switch transformer big is the MOE counterpart of the transformer big model, and it has a certain non-zero sparsity, and so are the last 3 models. So random search is going to be again one of the strong baselines that we will see. In random search, you essentially take the AutoMoE search space, but you do not do super network training. You take all the candidates that satisfy your latency constraint, take one of them and train from scratch. We are going to see the flops and the blue score. So the blue score is essentially the downstream task performance on this task. So the GPU hours shows the training time for 1 V100 GPU, which is normalized for 1 V100 GPU. And it is the entire end-to-end cost. For example, in case of the NAS methods, it would encapsulate the super language model training, the search, and the focused subnetwork training if you were to do any. And finally, the latency is measured on 1 Intel Xeon CPU. Okay. So the first thing that we see here is that the MOE models, again, switch transformer is the flops equivalent dense counterpart of transformer big. In this case, they have the same flops at similar latency. And we see that, yeah, the blue score is 1 point better. Again, these models are trained for exactly 40,000 steps. Switch transformer big is obviously a much more larger model, as you can see in the sparsity. So in order to get like sort of performance, you would probably need to train it longer with some kind of learning schedule decay and so on. Okay, so the next thing we see here is NAS over the dense models. For example, HAT in this case, it can find an efficient subnetwork which works pretty well with much less flops and latency. Now you might also ask that, okay, evolve transformer is also a NAS model. In this specific dataset, it doesn't do that good. But if you, for example, were to look at another task, for example, WMT 14 END, in that case, the evolve transformer was say 3.7x better than or faster than the original transformer big model, which also shows you that in evolve transformer, there is a big variance in performance as you apply it to multiple data sets. Okay. So then I talked about like random search. So AutoMoE search space, you have a latency constraint, randomly pick a candidate that satisfies the constraint, train from scratch, and you will see that it gets, in fact, the best efficiency numbers. But in terms of the blue score, the task performance, it regresses by 2 points. So neural machine translation task or any of the autoregressive tasks are in general kind of quite difficult tasks compared to say classification or natural language understanding tasks. So it takes a lot of effort, like just to improve by 1 blue point. So I would say that this 2 blue point degradation is actually quite a big regression in this case. Okay. So if we look at AutoMoE, we find in general that it reduces both the flops and the latency on an average by 4x on an aggregate. So it has parity in performance to transformer big, that is a dense model. But with regard to, say, the switch transformer big, we see a 1-point regression on an aggregate across all the tasks. So that also kind of hints at, as you scale up the size of the AutoMoE models for autoregressive tasks, we do see a gap that is due to the capacity, or like at least hints is due to the capacity gap between these two networks. And again, remember that these are very specific to autoregressive tasks. In case of NLU tasks, we can often obtain, say, 41x compression or so on with limited performance or no performance regression. But in case of any decoding or autoregressive task, it's kind of quite challenging to reduce the network size without losing this performance. Okay. So finally, we see that NAS over the sparse networks, like for example, AutoMoE is better than NAS over dense networks, which is, say, HAT. So again, AutoMoE has the same search space, same, say, implementation framework of HAT, and it just incorporates these additional AutoMoE specific search dimensions, like the notion of experts, of variable sizes, different layers, and number of experts, like the varying FFN blocks. But otherwise, it incorporates all the search factors that were present in the HAT search space for the dense networks. So essentially, the performance difference between HAT and AutoMoE is just due to the incorporation of the sparsity in the network. Okay, the last thing to observe here would be the GPU hours. So again, this is the end-to-end NAS cost, which is the total of the SuperNet training, search, and focus training. And we see that again, this is 40,000 steps for each model. And we see that this is not really more than training a dense model from scratch. Evolved transformer in particular, so we did not train evolved transformer, we trained all the other models. So the evolved transformer is an outlier here, which is also not based on a super language model training, which again shows that a SuperNet based training, which has an amortized cost, is massively cheaper than the progressive search in based methods like an evolved transformer. Okay. Now we will want to see like what kind of architectures do we get and is there a pattern. So the first thing is we are in an autoregressive task. Autoregressive task means that you are going to generate tokens one by one. So whenever I'm going to generate a token, I'm going to look at the last generated token, the representation from, say, the last layer for the previous token. So for every token, I'm essentially making a full pass through the network. So that makes the decoders to be extremely heavy, and it essentially consumes more than 90% of the overall latency. So what would be a trick to reduce the latency of the network in any autoregressive task is remove the decoder layers. So we have some parallel investigation explorations where we see that you should actually keep the encoder layers intact. In fact, if you reduce encoder layers, then you lose performance. And you can aggressively kind of remove decoder layers. So in all the settings that we have seen so far, we did not touch the encoder layer. So they were all 6 encoder layers, and we primarily made the decoder layers variably, all the baselines as well as our method. Okay, so the next question that you might ask is, where should you place the experts on the encoders versus the decoder? So the first figure here shows the number of encoder experts as a ratio of the total experts. Again, I said that we want to make the decoders light. Accordingly, the framework also puts most of the experts on the encoders and limited experts on the decoders. The last two essentially shows which layers should you place the experts. So for the encoders, we do not see much pattern. In general, we see that, say, the alternate layers and the middle layers are kind of have more experts, which is also something that is typically followed in practice, and this is something that we get out of the model, which is great. On the decoder side, we see that these are bottom heavy. So there are more experts on the bottom layers compared to the top layers. Again, why? Because we would want to, again, aggressively reduce the top decoder layers when we want to gain latency. Okay, and this is something that I mentioned before, that what would you search with, flops or latency? So here, if you look at the second block here, where the constant is 3 G flops, and this is like an evaluation on a very on a specific task, we will see that all the subnetworks we get, they actually exhaust the flops. And essentially, when these flops are exhausted, they give rise to decoder heavy models. And whenever you have decoder heavy models, you regress on the latency. So we found that the latency constraint is much better than the flops constraint, at least for the autoregressive nature of the NMT tasks. Okay, that brings to my last slide. So again, AutoMoE is the first work where we can principally design efficient sparse subnetworks, which answers all the different questions, like how many experts, where you can introduce them and their different sizes and so on. Haven't talked so much about dummy experts. So the idea behind dummy experts is you actually can have an identity function. You need not have a full FFN transformation to be applied to every token. So if there are some easy tokens, then it can skip the computation. And we actually found some evidence of dummy experts helping to reduce the flops with limited regression in latency. So AutoMoE, it supports adaptive computation. So adaptive computation, I have variable amount of computation for different parts of the input, which is largely given by variable size of the experts in the different layers, and also supported by our fully heterogeneous search space. Finally, like if you look at the overall result, we have 4x flops reduction and latency reduction over the traditional transformers, both big and the MOE variants. We have parity with the dense variant. We have 1 point regression on an average with the sparse switch transformer in general. And finally, we also studied some design policies of MOEs under resource constraints, like how should you design the layers, which like encoder versus decoder, which layers to inject, and what are the different trade-offs of flops versus latency versus active parameters and task performance. So you can find the code in this link and also the draft of the paper in this link.